So what is going to be the erythropoietin? How you are going to tell what is the nature of the erythropoietin? Because you all know that erythropoietin is a hormone, more of a hormone. And where erythropoietin is synthesized from? In the kidney, 90%. In the peritubular, interstitial, not in the tubules, non-tubular cells, interstitial, fibroblast-like cells. Fibroblast-like cells, typically near the proximal convoluted tubule. This is the usual location, but apart from these are the interstitial fibroblast-like cells. This is where you are going to get from the, this is where you are going to get the erythropoietin from. That is the reason why in interstitial kidney disease, because kidney disease is divided into many different things. For example, you have a tubular kidney disease, interstitial kidney disease, then you have polycystic kidney disease, then you have glomerular kidney disease. These are some of the etiologies of CKD and acute kidney injury. But if you ask me where the erythropoietin deficiency will be maximum, erythropoietin deficiency in kidney disease, erythropoietin deficiency in CKD, as well as anemia in CKD, anemia of chronic kidney disease. Where you ask me maximum, you will see in interstitial kidney disease. Interstitial kidney disease, since you are going to tell, erythropoietin deficiency typically happens in the CKD compared to AKA, you can tell chronic interstitial kidney disease. In a CKD, chronic interstitial kidney disease, you are going to get a maximum erythropoietin deficiency and hence you are going to get a maximum anemia. So all these are very important points. Where the remaining 10% comes from, the remaining 10% may come from the liver. So what is the most important determinant of erythropoietin secretion? What is the most important determinant of erythropoietin secretion? Is the oxygen tension that is seen in the blood and the tissues. Hypoxia, very important stimulator. If there is more oxygen tension, for example, if the oxygen tension in the blood and the tissues are more, erythropoietin secretion will decrease. The oxygen tension decreases, that is what we call hypoxia, then erythropoietin secretion will increase. We can see also the molecular mechanisms of how erythropoietin is increased or decreased. That's also very important. So what are the molecular mechanisms? So whenever you have a high oxygen tension, let us see that. So because there are two things that are very important in the form of an enzyme called PHT, then you have something called von Hippel-Lindau protein is there. All these things, how they interact with erythropoietin. So whenever you have a very high oxygen tension, increased oxygen tension, what is going to happen? You know very well that you are going to have reduced erythropoietin. Whenever you have reduced oxygen tension, you know very well you are going to have increased erythropoietin. You all know that. Though how the reduced oxygen tension increases erythropoietin is by increasing something called hypoxia inducible factors, typically 1 alpha and 1 beta. So this is the mechanism. They increase the hypoxia inducible factors 1 alpha and 1 beta. This in turn will increase the erythropoietin gene transcription and it will increase erythropoietin synthesis. But how there is a control, let us see. For example, whenever the oxygen tension is high, it increases the activity of one more protein called PHD2. It increases the activity of one more protein called PHD2. This is a hydroxylase enzyme. This hydroxylase enzyme does one important thing, that is, I told you there is something called HIF 1 alpha and 1 beta, hypoxia inducible factors. This PHD2 is going to hydroxylate this HIF 1 alpha and 1 beta. The moment this HIF 1 alpha and 1 beta are hydroxylated, this becomes a target for binding with another protein called VHL. That's called von Hippel-Lindau protein, comes from von Hippel-Lindau gene from chromosome number 3. You all know that already. So when the VHL binds with this HIF 1 alpha and 1 beta, they tend to break down the HIF 1 alpha and 1 beta. So which means this PHD2 hydroxylation facilitates the binding of HIF 1 alpha and 1 beta with von Hippel-Lindau protein. Then when VHL binds with this HIF 1 alpha and 1 beta, they break down the hypoxia inducible factor, resulting in reduced erythropoietin. Whenever there is low oxygen tension, the reverse happens, which means the activity of PHD2 is going to decrease, which means the hydroxylation of HIF 1 alpha and 1 beta will decrease, and because of that, VHL binding with the HIF will not happen, will be very much less. Because of that, you will have a very high erythropoietin release. So this is the reason why you are going to have a high erythropoietin in terms of hypoxia and low oxygen tension. So these are the molecular mechanisms. So that is also one reason why if you have a mutation VHL gene or if you have mutation PHD2 gene, if they are not functioning properly, then you might have a high erythropoietin release resulting in polycythemia. This is also possible. All these things are very, very likely you can get. These are some of the important things that you have to know about erythropoietin. Apart from these things, you also can know that where is the erythropoietin effect maximum. Erythropoietin receptors are maximally seen, and the erythropoietin effect of erythropoietin is maximally seen. All these things answer must be CFUE. As I already mentioned, it must be colony forming unit erythroid. At the same time, where you don't have EPO receptors, again as a revision, I already told you it is not seen in the reticulocyte and mature RBC. You don't see this. And what is the type of erythropoietin receptor? Erythropoietin receptor is something that comes under something called NRTK, that is called non-receptor tyrosine kinases, which means they are a Janus kinase. They are Janus kinases. So whenever you activate Janus kinase is whenever activated, this Janus kinase EPO receptor is a type of Janus kinase receptor. So whenever these are activated, you are going to cause STAT protein dimerization, because the STAT pathway you are going to have some cellular effects. So which means erythropoietin is a NRTK happening through, it's working through something called the JAK-STAT pathway. So this is a very important point. Not only erythropoietin, we already discussed in endocrinology. I told you already that TINS, TERS, GM-CSF and growth hormone. So TINS means erythropoietin, thrombopoietin, prolactin. TERS means interferon, interleukin. Then you have something called GM-CSF, granulocyte macrophage colony stimulating factor, and growth hormone. TINS, TERS, GM-CSF and growth hormone are acting through NRTKs or JAK-STAT pathway. So these are the cellular, this is how erythropoietin mechanism of action is all about. And what cellular effects you are going to get? They are going to increase the transcription of something called GATA1 and FOG1. This GATA1 is extremely important for erythroid lineage pathway. FOG1 is not that specific, but this GATA1 is extremely important for erythroid lineage differentiation. So that is the reason why this erythropoietin can increase the GATA1 transcription and increase the survival and lineage differentiation towards erythroid lineage. So all these things are very important things that you have to know about these things.
Subscribe and press the bell icon so you never miss an update from PrepLadder.